All right. Hi. Hi. How's calculus? All right. No comment? Okay. Uh, so how many do you have any tests left? You probably do, right? What do you have? Oh, that's fine though. So okay, all right, probably. Okay. So I want to do two things today. So one is we'll do one last sorting algorithm for now, just for fun. And then we'll start basically a new programming technique, recursion, which would be required for like, the crown jewel of this course in some ways, which is an actual fast sorting algorithm, the kind that Python actually uses. We haven't done that yet. But now I want to do the opposite, which is a very bad sorting algorithm, but it's kind of funny and it's fun to analyze. It's called Bozo sort. That is a name. It's on Wikipedia. So the idea is kind of like this. So you start with a list. Whatever. And then what you do is you swap two random elements. And then if the list is sorted, done. If not, you just repeat. Eventually, it's going to work out. So let's implement this, and then we'll analyze it. So we'll name this Bozo sort. So what do we need? So we basically say, okay, so if the list is sorted, then we're done. So we'll check if the list is not sorted. And if it's not sorted, we do the strategy here, which is take two indices. So I1 is going to be like this. This is the same kind of code that we had for computing pi, right? So here I have a random number that's between 0 and 1, not including 1. I'm stretching it to be between 0 and length of L, not including length of L. And then I'm rounding it down. So it's now an index inside of L. And I2 is going to be the same thing. And now we'll just swap L at I1 and L at I2. And that's it. So if we're done, if we exited the loop, that must mean that the list is sorted. So the only thing that I haven't done is sorted. So there's multiple ways of doing it. So the simplest way to write is sorted is to just say, L is the sorted version of L, but that's kind of cheating because we are writing an algorithm to sort. So like if we're using the built-in sort, that's silly because we already have it, right? But there is a faster way, I should say, of checking whether the list L is sorted, which is you go, pair of neighbors by pair of neighbors and see if they are in order or not. So that's the kind of thing that we actually did as practice for the midterm as well. So I'll say, like for I in range length of L -1, and I compare each of each pair of neighbors, L0 at 1, L1 at 2, and so on. You'll say if they're out of order. So if L at I plus 1 is smaller than L at I, so this would return true. So we mean like non-decreasing order, right? So non-decreasing means that can be increasing or there could be repetitions. So if they're out of order, though, then it's not sorted, so we return false. If we haven't returned false up until this point, we return true, so that's sorted. And That is the output. Make sense? So let's try it. So I'll say, both of sort L, and I'll print L, run it. Forgot the comma. Did forget the comma. Import random. And as you see, a perfectly good algorithm that produces a sorted list. If I do add a few numbers here, like maybe a 0 here and maybe 100 here, that's still okay. That produced like a small pause. And that is now going to take a while. So it's not technically an infinite loop because it's probably going to finish running, but possibly not in a while. So while it's thinking about how to sort this enormous list, let's think about why it takes a long time and how long it's going to take. So the analysis here is more sophisticated than what we usually do in this course, because really the answer is, well, it's going to be different amounts of time, different times. If you get especially lucky, maybe the list is already sorted, but even if it's not sorted, maybe you swap just the right elements fast so that it becomes sorted right away. So the best thing that you can do is to kind of guess at, like, on average, how long is it going to take? So one way to think about it, we're not going to do it super formally. This is just like an introduction, the kind of thing that I cannot ask in the exam because the formal analysis would be more difficult. So one way to think about it is we try different permutations of L. So a permutation, how many people know this word? Not very many. Oh, actually most people. Okay, did you learn it some? Okay, so a permutation is like a rearrangement of elements. And, an approximation is we need to try like n over 2 permutations. I don't even know how to spell it. Need to try n over 2 permutations until we find the one that makes L sorted, where n is the total number of permutations. Right? So what it's doing, it's like it keeps trying rearrangements of the elements until it finds the good one. So how long is it going to take? Well, like, you're probably not going to cycle through every which one, but there's no particular reason to think that you're going to find the right solution less than halfway through. So approximately like n over 2, where n is the total number of permutations. Oh, it's done. Amazing. Okay. So how many permutations are there? There is a formula. So the number of permutations of a list of n elements is n factorial. So to remind you, like 1 times 2 times 3 times n. All right. And there is a logic to it, which is you're saying, okay, like, how do I count permutations? I say, well, like, I have like n possibilities for which element goes on the extreme left, right? So that's like n possibilities to choose from. And then you also get to choose which element is number 2. So there's like n minus 1 possibilities for that. And there's n minus 2 possibilities for the third element and so on. So I'm not going to do it in detail. You can just like take it on faith that this is the number. So what this kind of means is that Bozo sort is approximately O of n factorial, where n is the length of L. And n factorial, of course, is a big number, right? So if you remember, and this is going to go nicely into our next topic. So n factorial is like this. So our length of L in this example was 12. Factorial of 12 is we need to start with 1 here. Factorial of 12 is this much. So it stands to reason that it took a while. And of course, you have a tiny little list of length, whatever, 40, and factorial of 40 is this much. Both sort is just not a very fast algorithm. Make sense? All right. So that was sorting for now. Questions about any of this? So to highlight, what do you need to know? What do you not need to know? Here. The analysis here, not really, because we did it informally. So, and there was some hand waving there in several places. We are not actually doing permutations in random order. We are adjusting the ordering a little bit. That matters, not by a lot as it happens, but it hello? I believe we're back. So we're talking about recursion, and what recursion is functions calling themselves as helper functions. So here is the example that everyone starts with when they start talking about recursion. They start talking about factorials. So n factorial, we defined it in a way that kind of looks like it's a for loop, right? So it says I equals 1, I equals 2, I equals 3, and so on. But another way to think about it is n factorial is n minus 1 factorial. So 1 times 2 and so on times n minus 1 times n. Right? So that just follows mathematically. This and this, those are the same. Does that make sense? Questions? So, okay. So what that means is we can say, okay, so here we wrote it in algebraic notation, but you can also write it in Python style notation to say that factorial of n is equal to factorial of n minus 1 times n. Right? So I'll just rewrote the algebra into something that looks more Python-y. Not quite Python-y because really this is equals if you want to be strict about it. Right? So what we can do is instead of using a for loop, we can write the function like this. This is not complete, but this is the basic idea. So what I'm saying is I want to compute factorial of n. I know that factorial of n mathematically is equal to n minus 1 factorial times n. So I'll just call my factorial function with n minus 1 multiplied by n and return the result. Mathematically, that must work out. Okay, so one more thing that I need to do here is I need to have what's called the base case. So the issue is that when n is equal to 0, that makes no sense. Like factorial of 0 is not 0 times factorial of minus 1. Factorial of minus 1 is not even defined. And factorial of 0 traditionally is considered to be 1, not 0. So what we need to say is, well, like for a small n, I'll just say what it is. So I'll say, for example, if n is smaller or equal than 1, then I just put in the answer. I'll say 1. All right. So that's the complete function. So that works. We can compute factorial of 40 again, and it's going to be the same number. So the same thing. So why does it work? One way to think about it is, well, it must work mathematically because this is a correct formula. And what we did is we used this formula. Another way of thinking about it is saying, okay, I'll check that it works for 1, and I'll check that it works for 2, and then I'll check that it works for 3, and so on. So, okay. So we'll just do that. So factorial of 1, what is it going to do? Well, it's going to check, is it small or equal than 1? Yes. Return 1. So it'll return 1. So the weirdness here didn't even happen because you get to return 1 right away. What happens with factorial 2? Well, what happens is 2 is not small or equal than 1. So you'll return this. So what is this? Well, this is factorial of 1, 2 minus 1 times 2. We already know what factorial of 1 does. We checked. This is 1. And you can see why, because it returns 1 here. And this is just times 2, so that is going to be 2. We'll write it as like 1 times 2. So then what is factorial of 3? Well, this is not going to happen. So factorial of 3 is going to get to this line. And then what is this line? Well, this is factorial 2 times 3. What is this? Well, we already thought about what happens when you call factorial 2. What happens is you return this. So that means that that's going to be this 1 times 2 and then times 3, which is 3 factorial. We'll do just one more. So factorial of 4. Again, you get to here. So this is going to be factorial of 3 times 4. And factorial of 3, we already know what it is. It's this guy. We already computed it, right? So factorial of 4 is going to be this guy times 4. Which is, of course, exactly what we want. Like it works out that what you get for factorial n is 1 times 2 times 3 and so on times n. Make sense? So, okay, all right. So here are the components of a recursive function and their names. So this is called the recursive step. And this is some kind of thing, kind of the answer in terms of the function itself, right? So like we're using factorial as its own helper function. In general, like that's what recursion means, is that you have a recursive step, right? This is what's called the base case. And this is the answer when it's known. And that prevents infinite recursion, right? Because if you didn't have something like this, then you would keep saying, okay, a factorial of 2 is like factorial of 1 times something, is factorial 0 times something, is factorial minus 1 times something, is factorial minus 2 times something, and it never stops. So the base case must be set up in such a way that this doesn't happen. Make sense? How? Well, like, you got to make sure it's different depending on each situation. So in other words, you have done the don't push on a rope thing this year, right? Yeah. Okay. So yeah. So like there's like the 3 rules of recursion. Okay. So you cannot push on a rope. So must have a base case. Because like no base case basically means like you're like infinitely trying to push in a rope. It works out really nicely. The second rule would be to get the answer, you must know the answer. And that would be the recursive step. That's the third rule. And the third rule is F equals MA. There's no third rule. So, yeah. All right. But those things work out. Those things kind of work out really nicely. All right. Okay, questions so far? So we'll do obviously some more examples now. All right. So let's do an example that's almost like this. So we want to return x to the power of n. So one way to do it is, again, with a for loop. We've done it with a for loop, but you can also do it with recursion. So you just want to figure out, okay, so like, how do I express x to the n in terms of something that's like the power? There's actually several ways. But the most straightforward one is the same kind of thing as what we've done with recursion, right? So we'll just say, well, x to the power of n is x to the power of n minus 1 times x. Make sense? So to express x to the n in terms of power, we just say, okay, so let's return, we'll say power x to the n minus 1. So this would be x to the n minus 1. And we multiply it by x. Okay? And the way to think about it is, this is just the formula. We got to have a base case. What's a good base case, anyone? Yeah. Yeah, exactly. So x to the 0 for anything that's not x equals 0 is 1. So just assume that x is like not 0, whatever. So like 0 to the 0 is like usually considered not defined anyway. So we'll say if n is equal to 0, so we want to return x to the 0, which is equal to 1 for everything that's not 0. So we just return 1. And in the same way, like if you want to compute x to the power of 1, well, that's going to be x to the power of 0, which is 1, times x, which is x. So you return x. Make sense? So, all right. We're not going to do complexity of recursive functions just yet, but I want to give you a preview. So there is a trick to compute powers faster than this. And the trick is kind of like this. So let's say that I want to compute x to the power of 16. So one way to think about this is, well, like I got to multiply x by itself 16 times, whatever, like if you start with x 15 times, right? But another way of thinking about it is x to the power of 16 is x to the power of 8 squared. Just math, right? And that is x to the power of 4 squared again. And that is x to the power of 2 all squared all squared. The reason this is nice is that this is just 4 multiplications, right? Because to compute something squared, I just multiply it by itself. So if I just do square 4 times, I guess it would be square. Then instead of doing whatever 15 multiplications, I can just do 4. Make sense? So how can we express it using recursion? So if we get lucky and this is like a 16 kind of thing, what I can say is x to the n is equal to x to the n over 2 squared. Right? Does that make sense? So one way in which I might not get lucky is that if n is an odd number, then mathematically this is still true, but computing x to a fractional power is more trouble than what we want for today. Right? So, okay. So what we'll do though is we'll basically say, okay, so like there's 2 situations. There is a situation where n is even. And then this is just true. And then the other situation is n is odd. And then what we got to do is we got to say, okay, so we'll divide n using integer division. And then we'll square it back. But if we divide it using integer division and we round down as a result, this would not quite get us back to x to the n. Right? So I'm first working out the example, then we'll write it down in normal order. So if I want to compute like x to the 7, then that would be x cubed squared, but I need to remultiply by x because I lost a power of x by rounding down. Does that make sense? So here, what we want to do is we want to remultiply by x. Make sense? So, okay. So that gives us the answer to what x to the n is in terms of the power function again. So again, we need to return 1. We also will come back to this, but we also need to return x if n is 1. And now that we're done with it, we can say, okay, all right. Is n odd or is n even? So we'll say if n is even, I'll compute the half power. So this is power fast x to the n over 2. The reason this is integer division is I want for this to always be an integer. So even though n is even, I'll do integer division. And I'll return half power times half power. If n is odd, the half power is the same again. We'll take it out of the if statement in a second. But we return half power times half power times x. So because this is defined twice, we can just take it out of the if statement and put it here. All right. Why did I do the half power instead of, just saying power fast x n over 2 times power fast x n over 2? Well, that would defeat the purpose because I would be computing, well, not quite, but like I would be computing x to the power of n over 2 twice, and I'm trying to save on multiplications here. Yeah.
For the odd case, is it fine if we also do like power fast and then x and minus 1 times x, like basically what it was before for the odd?
So I mean, yeah, because so here it's like it automatically here does exact division for an even, and it does round down for an odd. Right, so that's like I also wrote it here. So like this is where the rounding down happens if n is odd, and because of that, I need to like post multiply by x. Is that making sense? Questions? Feel like people are tired today, and that's not even accounting for the people who are not here. So... All right. So, okay. So because people are tired, I'm not going to do the complexity analysis. Yeah. I think you're asking about this part. Oh, yeah. So basically, the alternative was to say something like return this times this. And well, like in order to do that, like you'd compute this and then you'd compute this and then you'd compute the multiplication. So you're obviously wasting a lot of time, right? Because it takes some amount of time to compute this. You need this value twice. So like there's no reason to compute it twice. So there is a formal analysis for exactly how much of a slowdown it is. We're just not doing it today. It is a bit of a slowdown. So informally, I'm just gonna like as a spoiler. So this is O of log n. If you do it like this, it becomes O of n. So all the savings that we get from not doing the multiplication n times basically go away. But for now, it's just like the intuition is this is obviously a lot fewer multiplications because basically you're doing something like this. So for x to the 16, you're doing 4 multiplications instead of doing 15 of them. Make sense? All right. Let's do a few more examples. Let's see how many we can do. So let's say that I want to sum a list. So by the sum of the list, I just mean like literally like the sum of all the elements in the list, right? So how can we define this mathematically? Well, one way to say it is if I want to sum this kind of list, well, that's the sum of one, the first element, and this list. Does that make sense? So like it's got to be the case. Like you take you take the first element and then you take the sum of the rest of the list. That's the sum of the whole thing. And then that's going to be 1 plus, so the first element here, and then the sum of the rest. Make sense? So if I want to write it as a kind of formula rather than with just an example, I can say that the sum of the list L is the first element of the list plus the sum of the rest of the list. Right? Does that make sense? Just like as math, like it's got to, right? Like the sum of the whole thing is the first element plus the sum of the rest. So, okay. So what we do is we just copy this over here. Because mathematically it's true, so we just return it. What's a good base case? Like when do you know the answer to what's the sum of the list without thinking too hard? Yeah. Yeah, or better yet, a list of no elements has nothing, so that's just 0. One element would work as well. So just say if the length of L is 0, we just return 0. We just define the sum of the empty list as 0. We could say, well, like the empty don't really know. Like you were suggesting, we could say if the length is 1, then the sum is just L at 0. Make sense? So that's one way of doing it. I assure you it works, but just to make sure, it is 6. So why does it work? Well, because what you're doing is you're basically computing the sum step by step. Make sense? So can you think of a different formula for the sum of the list that's kind of analogous to the trick here? Anyone? You could do that. I'll do that next time though. It's a good idea. Sorry, not next time. This is actually going to be in the lab, kind of. So another idea. So I want the sum of the whole list. How do I get it? By like looking at like a smaller problem or 2 smaller problems. Well, you can take like the first half and the second half and then add them up. Right? So you can say as well, so the sum is the sum of the first half plus the sum of the second half. So the nice thing about the Python notation is that it works out, right? So here we're saying everything up to but not including this guy. And here we're saying everything starting from this guy and up to the end. So, okay, so we'll just do that. Again, I'm just copying and pasting. So here, let's pay a little bit, I'll call it sum list 2. I could, of course, mix and match if I wanted to. But here I'm doing like sum list calls sum list and sum list 2 calls sum list 2. So first of all, let's see what happens if I just call it. So that's going to be taking a while because I did not put in the base case. So here it just crashed. It crashed by saying maximum recursion depth exceeded. So basically it called itself 1,000 times and then it got tired. But really, this is an infinite loop. Make sense? So does it make sense? Why? Because we keep calling it and then eventually we call it with an empty list, but that doesn't stop it. It keeps calling like sum list of the empty is like sum list of the first half of the empty plus the second half of the empty. And then it tries to compute sum list of the empty again, and it never stops. So we could try doing this. And that did not quite do it. So we still get infinite recursion. And the issue is that if you think about it, when the length of L is 1, how do you break it down in half? Well, the first half is empty and the second half is the rest of the list, which is 1. So you're going to be computing the sum of the list of length 1 as the sum of the empty, which is 0, plus the sum of that list again, and you keep computing the sum of that list. So here you also got to stop if the length of L is 1. And now that works, we just didn't print. So that's 6. That was so that was like probably too fast. But we don't have time to go through it. So we'll start tomorrow by going through this example and making sure that we know why it is that we had to do this. I did not explain it yet, although you can figure it out. All right, I will see you tomorrow. Bye. Thank you.